Okay, guys, let's go ahead and talk about it's not hoarding. The quote we have is, "I'm positive I've lost an electron. I better keep an eye on that." When we're talking about this, we're talking about ionic bonding. And in ionic bonding, what happens is we do create ions. So let's dive into it. Now, our learning goals for this. Students will understand the nature of ionic bonds. So we need to know what an ionic bond is, what makes an ionic bond, and how to tell the difference between an ionic bond and covalent bonds and metallic bonds and things like that. Number two, students will move from name to chemical formula and vice versa for ionic compounds. So we want to be able to look at a name and be able to write the formula, and look at the formula and be able to write the name. So go back and forth on both of those. And then lastly, students will be familiar with differences between ionic and metallic bonding. So we'll briefly talk about metallic bonding in this, but we'll need to know the difference between those two. So, the first thing we need to revisit is the octet rule. Now, atoms are most stable with a filled orbital shell. And what this means, remember that in the electron configuration, when we have our s orbital and our p orbital, remember s can hold 2 electrons and p can hold 6. Okay, when the s and p are completely full, we have a total of 8 electrons. These 8 valence electrons, and remember what a valence electron is, it's an electron in the outermost energy level. But when we have these 8 valence electrons, the atom becomes stable. It becomes happy. It becomes, basically, you can think of it becoming more comfortable there. Okay, and that's where it prefers to be. Now, elements with atomic number that are less than 36 follow that octet rule. Okay, so everything below 36 or less than 36 will follow that octet rule. And then hydrogen and helium are the exceptions to that. Okay, so they're obviously, they have a lower atomic number than 36. They're 1 and 2, but they are stable with only 2 electrons. Okay, we call this the duet rule. And the reason why they're stable with 2 electrons is because in that first energy level, you only have an s. Okay, it's 1s. And so in that first energy level, when they have those 2 electrons, that energy level is completely full. So they're stable like that. And so since it's completely filled in that orbital shell, in that 1s, they're happy. They're the exception. They only have to have 2. That's our duet rule. Now, when we're looking at these, noble gases satisfy the octet rule, meaning everything wants to be like a noble gas. The reason why the noble gases are so stable is because they already have that octet. Okay, they're so stable, they don't bond with anything, they're unreactive because they don't have to gain or lose or share electrons to become stable. They already are stable. They're stable by themselves because they already satisfy the octet rule. Okay, now our alkaline metals, that's our group 1. For stability, they can either gain 7 electrons or lose 1 electron. So obviously it's a lot easier to lose 1 electron. And if you look at the noble gas notation for any of our alkaline metals, what you'll see is you'll have a noble gas, whichever it is, and then you'll have S1. Okay, so like for sodium, we have neon as the noble gas behind sodium, and then neon or sodium is 3s1. So if you think about it, if it gets rid of that 1 electron, there you go, it's neon. It has 8 valence electrons. It's happy. Okay, now our alkaline earth metals, they have the option too. They can gain 6 to get 8 or lose 2, which we see if we're looking at, let's see, sodium's neighbor, it's magnesium. Well, that's neon, and then that's 3s2. So it can either gain 6, or if it loses 2, it becomes the noble gas, and its electrons have the same structure as a noble gas. Okay, for our calculons, what we see is that the oxygen family right there, what they have is, to become a noble gas, they can either gain 2, so anybody in the oxygen family can gain 2, or they can lose 6. Okay, what's easier? Gain 2, lose 6. Well, gain 2, obviously. And if you look at anything in that family, what it's going to end up with is going to have an S2 and then a P, and we'll see a 4. So if it gains it, what it'll end up being is it'll end up being that S2P6. Okay, and we know that when our S and our P are completely full, that means we have 8 and they become stable. Okay, for our halogens, they're really close to being a noble gas, these guys right here. And so all they have to do is just gain 1 electron, or they can lose 7, which we know that gaining 1 is much easier than losing 7. Okay, so what we'll have is we have our cations, which are group 1, 2, and 3, are more stable with less electrons. Okay, so anything in group 1, 2, or 3, what they'll end up doing is they'll give up all of the valence electrons that we have to become more stable. So an example, lithium, it gives up. It is in our alkaline metal group, and it gives up. It's in that group 1. It gives up 1. It becomes more stable. It's happier once it's lost that electron. Okay, because once it loses this guy right here, it goes back down, and its energy level is full. It's happy. Okay, and so that whole energy level is filled, and that's the way it is. So instead of being in this shape up here, loses that 1 and becomes more stable. Okay, if we look at anions, anything anion in group 15, 16, or 17 are more stable with more electrons. So if we look at this, our two options. Okay, and this is fluorine, so it has 1, 2, 3, 4, 5, 6, 7. Okay, and it has 7, so it needs 1 more. So once it gets to 8, it becomes more stable because it's full. So let's look at an example. It says, how many valence electrons does a stable sulfur atom, anion, have to have? And so what we need to do, the first thing I want us to write down here is something that we call the hill of oxidation numbers, just so that we can have it. Okay, gets us kind of like a hill that looks like this. And what we get is we get group 1, group 2, group 13, group 14, group 15, group 16, and group 17. Okay, and our oxidation numbers, what we have right here, there we go, and our oxidation numbers are going to be what they normally do. Okay, well, anything in group 1, 2, or we call R13, those guys want to give those up. So this is +1, +2, +3. Now group 14, it's kind of in the middle. It can either gain 4 or lose 4, so it kind of can go either way. So it's plus or minus 4. Now our group 15, they already have 5 valence electrons, so they only need 3 more. So -3, -2, and -1. And so when we look at this, what we'll see is we look on our periodic table, and let's scroll back up here to look at a periodic table, and we'll see that sulfur's right here. It's in group 16. So if we look at our hill of oxidation number, anything that's in group 16 is more stable once it loses 2 or gains 2 electrons. So what does it have to do to become more stable? That anion. So what we would draw it as is we have our sulfur, and then we have a 2 minus or a -2, either way you want to write it, and that would be our charge for it. That's the anion that makes it the most stable. Okay, now that we've looked at atoms and what makes them more stable once they get that octet, and giving and losing electrons, we're going to talk about ionic bonding. Now we're going to talk about it in terms of Coulomb's law. Basically what it boils down to is opposite attracts and like charges repel. And so like charges, the closer they get together, the stronger the force it is that pushes them away. And like charges, the closer they get together, the more they are attracted to each other. And so what happens is we have these opposite charges. And in an ionic bond, what you'll have is you'll have that positive charge from a cation and a negative charge from that anion. And what you're going to get is you're going to pull each other really, really close. And what this makes is it makes an ionic bond that's very, very strong. Okay, now what an ionic bond is. An ionic bond forms between metals and nonmetals. It's an extremely strong bond. Okay, that means it's going to have very high melting points. That means it's going to require very large amount of energies to break it up. So when we're looking at this, basically what happens is when we have this electron wants to give to the fluorine to make this have a complete outer shell, and fluorine, by taking it, will have a complete outer shell. And so therefore what we get is we get this really strong bond. Sodium will become positive and fluorine will become negative, and that positive and negative pull each other together, and they like to stay connected to each other. Okay, so let's look at an example. It says an ionic bond is stronger than other bonds, and explain using Coulomb's law why this is the case. So as that electron moves, this atom becomes positively charged and this atom becomes negatively charged. And as the distance between them decreases, what we'll see is the force of it increases. And what we'll see is the force in that Coulomb's law, opposite attracting positive and negative, that it keeps it bonded together and makes it very, very strong. Now, what we previously looked at was we looked at one singular atom. Okay, actually two atoms that are bonding together to make a singular compound. Now, what happens is normally things don't exist as one singular compound. What happens is they usually exist in compounds together. So many compounds around each other. So what we have is that in ionic bonding, we have what is formed a crystal or a crystalline lattice. And basically what we get is we get that positive and that negative, but basically what happens is when all those positives and all those negatives get together, these two are bonded to each other, but what we see is that since this becomes negative, well, it has a positive right underneath of it. And this positive has a negative underneath it and to the side. And so what you see is in this crystalline lattice, what you'll see in ionic compounds is that you'll see that every positive is surrounded by a bunch of negatives, and every negative is surrounded by a bunch of positives. And what this does, it creates and makes very, very strong bonds, and it gives us that really high melting point, really high boiling points, very, very strong. They're solid at room temperature because of this crystalline lattice structure, but ionic compounds are very, very brittle. And what this means is that if we push this compound over, okay, that negative over, and what happens is this whole row up top shifts. Well, now a negative is over a negative, and they don't like each other. So basically, that makes them flake off, and that breaks the ionic compound. Okay, and basically you have a big chunk of, we can say, salt, and if we can take it and break pieces off of it. Okay, it still has a very high melting point, still a very high boiling point, but it makes them very brittle where you can break them. So let's look at an example. If you're given a solution containing both ionic compounds and a covalent compound, using the properties of ionic compounds, how could you separate the two out? Well, one of the easiest ways to do it is if we know it has a very high melting point and a high boiling point, what we do is we take the solution and we go ahead and we call this, it's called an evaporation technique. We take the solution, we put it underneath a Bunsen burner, or on top of a Bunsen burner actually, and it boils off the liquid. And since the ionic compound has such a high boiling point, it'll stay trapped in there as the water goes away. Okay, now that we've talked about stability in atoms and we've talked about ionic compounds and how ionic compounds exist, let's look at naming ionic compounds. And this can be naming and it's formula writing. And so naming ionic compounds, these are the kind of steps that we take when we're trying to name ionic compounds. In step one, we first write out the cation, and then we write the anion second. Now, cations consist, and I would make a note here, cations are normally going to be our metals. Okay, anions are normally going to be our nonmetals, or they can be polyatomic ions. Okay, but basically what we get is in an ionic compound, it is a metal plus a non-metal, and that's how we tell the difference between those. Okay, in metallic bonding, it's between a metal plus a metal, but in ionic, what we see is that we're going to have it between a metal and then a non-metal. So a cation will be the metal and the anion will be the non-metal. Now, the charges must balance to 0. So basically we can't have a charge to it. So if the metal is going to have a +1 charge, the non-metal's got to have a -1 charge. They have to balance each other out. Or if we look at the metal has a +2 charge, then the non-metal has to have a 2 -1 charges, which balance that out. And we'll look at that in detail in just a second. And then number 4, this is a reference to covalent bonding, which we'll talk about later, but prefix units are not used. So we're not going to use any prefixes here. And that'll make a lot more sense when we talk about covalent, but always keep this in mind. We never use prefixes in ionic bonding. That's only for covalent bonding. Now, number 5, if the cation is a transition metal, the charge is specified with a Roman numeral. The interesting thing about our transition metals is that our transition metals can have different oxidation numbers. Okay, when we wrote the hill of oxidation numbers, we did group 1, group 2, group 13, group 14, 15, and 16, and 17, because those are the ones that don't change. Oxidation numbers of transition metals change, so we'll look at that too. And number 6, if the anion is an element, the end is replaced with an IDE ending. If it's not an element, we just write the polyatomic ion and then put its name. So let's look at an example. Now, when we're looking at this, this is going to be a bond between lithium and oxygen. So the first thing we do, we already have lithium and we have oxygen written. Okay. The next thing we do, we write down their chemical symbol, which this is lithium and that's oxygen. Now, where we got these plus and minuses, that comes back to what makes them stable. So when we looked at our hill of oxidation number, we looked and we see that our lithium is in group 1, so that's why it has a +1 charge, and oxygen is in group 16, and that's where we get the -2 charge. And this is what we just get from the periodic table. So once we have those, what we do is we take them and let's get that out of the way. And what we do is we crisscross them. We cross the charges for the subscripts. Okay. Now remember what I told you. The positives have to balance out the negatives. When we crisscross like this, we bring this 2 down and that 1 down. So that 2 went right here and that 1 went right there. It's just understood. We don't have to write the 1. We just leave it understood. But what we see is that, remember what I said, the charges have to balance out. So how many lithiums do I have? Well, I have 2. What's the charge of lithium? +1. So we have +1 and +1. And then oxygen, how many do we have? 1 of them. What's the charge of it? 2 negative. Well, the positives balance out the negatives, and we got a charge of 0. By crisscrossing, we get a charge of 0. Now all we have to do is name it. This is lithium. It's not a transition metal, so we don't need to put a Roman numeral for its oxidative state. And then we have oxygen, which we replace the ending of oxygen with IDE, and that's where we get oxide. So let's look at some polyatomic ions and what they are. Polyatomic ions, they're atoms that are treated as a single molecule. They can be both cations and anions, so they can be positive and they can be negative, and we need to memorize these. We have to have some of them memorized, the common ones, and we'll have a list of those that we'll memorize. But basically what happens, we got to have them. So when we talk about nitrate, nitrite, when we talk about phosphate, phosphite, we know what the formula is before we move on. Okay, let's look at some examples. This is a tough one. So it says the professor for your chemistry lab forgot to record the oxidative state of copper used to create copper sulfate. An in-depth mass analysis provided the empirical formula. Based on the available data, what is the oxidative state of copper? So how we named this? Well, it's very simple. We looked at Cu. Guess what? That's copper. We looked at SO4, and we know our polyatomic ions because we have them memorized, and we know that SO4 is going to be sulfate. Okay, so we have copper and then we have sulfate. So that's where we get it right here. Now remember what we said in our rules. If it is a transition metal, it has to have a Roman numeral to specify the oxidative state. So yes, this is copper sulfate, but we need to figure out what is the oxidation number of copper. To do this, very simple task. Okay, what you're going to do, we know the oxidative state of sulfate because we memorized our polyatomics. We have SO4 with a -2 charge. Okay, so what we do is we set up the whole compound is going to be equal to 0. Okay, so 0 equals all the charges have to balance out. How many sulfates do we have? 3. 3 times its oxidative state, which is -2. 3 times -2 is -6. Okay, plus the other part of it, copper. Now, how many coppers do we have? We have 2. Do we know its oxidative state? No, so we just go X. So it's 2X. And then all we have to do is solve for X. So we bring the 6 to the other side, and we have 6 equals 2X, and then we divide by 2, and X equals +3. Now how we write the name? We write copper 3, 1, 2, 3, and then sulfate. And we only have to do this when you have a transition metal. Okay? Next example. It says write the correct molecular formula for barium oxide. So when we're looking at this, we look at our hill of oxidation number. Okay, look at your periodic table, and we'll look at it. Let's scroll back up, find a periodic table, and almost there. There we go. So here's barium. It's right there. What group is it in? It's in group 2. Okay, so when we look at our hill of oxidation number, we see that it is in group 2. So barium, which is Ba, will have a +2 charge. And oxygen, pretty common. We see that that's going to be in group 16. So oxygen will have a -2 charge. So all we have to do here is crisscross them to write the formula, and we get Ba2O2. When this happens, when their oxidation numbers are the same, you see how this is a 2 and that's a 2, you can reduce it to a 1 and a 1. So instead of having Ba2O2, you can reduce these down to a 1 and a 1. So barium oxide is just BaO. Now, ammonia hypochlorite. Okay, so ammonia, or ammonium is going to be NH4. It's a polyatomic ion. It has a +1 charge. Now, hypochlorite is going to be ClO with a -1 charge. So all we have to do is crisscross these guys, bring the ones down, and what we get is we'll get our NH4 1 ClO 1, and we get ammonium hypochlorite. Now, since they're just ones, we don't need to write them. We can just take this away and just leave our formula as NH4ClO. Let's look at our last couple examples. It says write the proper name for, and then we see we have Ki, and then we have SnClO4. So on our first one, it's 2 elements together. Okay, the first one's potassium. So the first thing we do is we write potassium. Okay, we check, is potassium a transition metal? No, so it doesn't need a Roman numeral. So we look at the other one that we have, it's I, which we know that I is iodine. Now, anytime we have an ending and it's an element, and the anion is an element, what we do is we go ahead and change the ending from iodine to iodide. We put an IDE ending. So on our first one, we get the name of potassium iodine or iodide. And we see on the next one, we have SnClO4. Now, again, we're going to go ahead and name these guys. The first one, Sn, we look on the periodic table, it's 10. Okay, now the ClO4 is a polyatomic ion. That's perchlorate. We also, you can see it called hyperchlorate, but we're just gonna write perchlorate. And since it's a polyatomic ion, we don't have to change the ending. Now, tin is not a transition metal, but tin does need a Roman numeral because tin can have multiple oxidative states. So it can be tin-2 or it can be tin-4. So to figure out what it is, we know that the whole compound is going to be 0. So 0 equals, and then we look at this. Chlorate or perchlorate is going to have a -1 charge. Well, how many do we have? We have 4 -1s, so that'll give us a -4. Plus the oxidation number of 10, which we don't know, so we only have one of them, so it's just 1x or x. So to solve for x, all we have to do is add 4 to both sides, and we get +4 equals x. And so what we do is we give the Roman numeral 4 to 10. Okay, so we get parentheses 4. So this becomes 10,4 perchlorate.